So thanks for coming. I think we'll kick it off. I'd like to have Dr. Josh Marshall, our Institute Director, kick us off for the day. Thanks.
Thanks everyone. Thanks for being here. How many people were here at the CRC event yesterday? Please put up your hand. Okay, like a lot of people, great, and thank you for staying today. Hopefully you all get out to see what it looked like at Ingenuity Labs. Today's a little bit about a showcase, I guess, to a certain extent, so you get to kind of hear a little bit about what's going on at Ingenuity Labs. These pictures are from yesterday, for those who weren't able to make it. A lot of smiling faces and a lot of great discussions that I think happened around the table. We are about, for those who don't know, and I know a lot of you in the room already do know, but for those who don't, we're about 8 years old now. Ingenuity Labs started on the basis of a pretty large donation from one of our alumnus, Bruce Mitchell. And our vision at the time, and this, like keeping in mind, this was 8 years ago, okay, maybe not that long, but at the same time, kind of long ago in the sense that we had this idea that AI and robotics should really be coming together. And at Queen's, we were big enough but small enough in the sense that we have people working on this space across the campus, and yet we weren't really working together. We were a little bit siloed, and so the idea was to bring together robotics and AI into a research institute where we could easily collaborate, where we could work together, we could share some open space, we could remove sort of the financial barriers maybe in some sense and make collaborative projects work on the financial end, and we've kind of been successful at that, I think. I think we've had some wins and some things we still have to work on. But when I look back and I look at the news, I think, you know, we were on the right track. We had the idea of putting robotics and AI together, and if we look at the news today, I do wonder whether we had the right name, though. We called ourselves Ingenuity Labs. We struggled with the name. What should it be? We had all sorts of names. The one name we did not come up with was the Institute of Physical AI. And so maybe we should have called ourselves the Institute of Physical AI. I don't know. And that is something maybe we'll talk about today when we have two debates. So we do have, as per tradition now, and this is our fourth, Ingenuity Labs Robotics and AI Symposium. We have a keynote speaker, which I will introduce in just a moment. And we have two debates, so hopefully most of you will be able to stick around for the whole day because it's going to be fun. I think we have a robotics debate first, and some fun, I think, discussions going to happen around what we need to do to bring robotics and AI together, and what is sort of the challenges of the future for robotics, and how can we do this in a coordinated way. And then our AI debate. So if you missed it, there was a QR code earlier. Hopefully people have found the agenda and times, but Ramsey will try to keep us on track. Okay, so obviously I'm just going to give a brief intro to sort of what's coming. Obviously AI is at the top of our minds these days. The hype is enormous. Large language models, ChatGPT, changing everything. Discussions suggest we're on the brink of some sort of age of AI-driven society. Then again, we have these sort of geopolitical situations around the world that are raising issues, and some disillusionment is starting to happen around AI. And I think some of the things that we're seeing on the news and both pro and con AI are going to be the subject of today's debate. So the question is, are we there yet? Is AI discovering new things in frontiers, or are we sort of just wandering around in circles? What's going to happen? So we're going to debate that. And then we have our robotics debate, and it's really about a national robotics strategy. And I think yesterday, for those who were here, we heard a lot about this, and we talked a lot about, like, what should we be doing together? And that's going to be the discussion today. Are we leaping forward? Do we need a strategy, or is pursuing sort of a national robotics strategy a futile pursuit? Do we already have this? Is it maybe already there in some different spaces? And I think we're going to hear arguments on both sides of that. So stay tuned for that. I think that's going to be an exciting event this afternoon. Or sorry, rather later this morning. That's the first one up at 11 a.m. And then last but not least, but first on the agenda, is our keynote speaker. So it is my great pleasure today to have Dr. Elizabeth Croft join us from University of Victoria to kick us off. Somebody that I have actually admired for many, many years as a roboticist. For those of us who have been in the robotics space for a long time, we all know Elizabeth's work over the years. I have a little bio here that I think I do want to read because it is quite impressive. So Dr. Croft is a visionary, I think, and forward-thinking leader with a track record of building inclusive, collegial, collaborative partnerships. And honestly, this is very, very true if you know her work. On July 1st, 2022, she bravely began, and I put those words in myself, a 5-year term as Vice-President Academic and Provost at UVic. So we managed to pull her away from Victoria in her provostial role to come all the way to Kingston. However, first in my mind is that Dr. Croft is recognized internationally as an expert in the field of human-robot interaction. So before joining UVic, Dr. Croft was the Dean of Engineering at Monash University in Melbourne, Australia, and prior to that, she was a professor in the Department of Mechanical Engineering at the University of British Columbia. And in each of her many senior roles and positions, her action-oriented approach has delivered results in areas of importance to universities, including innovative academic programming, reconciliation and decolonization, transformational student experience, and in particular, I think, equity, diversity, and inclusion. So we'll hear maybe a little bit about what her research is about and how it relates to those items, I think, today. For 5 years, Dr. Croft was the MCERC Chair for Women in Science and Engineering for BC and the Yukon. And in this role, she delivered policies and outcomes to increase the participation of women and other equity-deserving groups in engineering with significant and measured success. Her outstanding contributions have earned Dr. Croft considerable recognition, including the Society for Teaching and Learning Higher Education Alan Blizzard Award, WXN's Top 100 Most Powerful Women in Canada Award, and the Engineers and Geoscientists BC R.A. McLaughlin Award, among others. I can't say enough, I think, about how grateful we are to have you here today, Dr. Croft. Please join me in welcoming Elizabeth Croft to the stage.
Okay, thank you so much, Josh, for that really warm welcome. It's nice to get out of the house when you're provost and come and be with folks who care so much about the things that I care about in robotics. So today I'm going to be talking about some work that I've been doing with graduate students at UBC and at Monash and working with colleagues at UVic. And it's really about human-robot communication, because I think in all of the hype, in all of the things that we're thinking about all the amazing things we can do with robots now and with AI, centering people in how people and robots are going to relate is going to help us move forward, because in the end, we are doing these things, we work in this area to advance society and help people have better lives and help people be more effective in their work. And so making sure that people and robots can work side by side, effectively understand each other. It's really been the thing that I've been thinking about all my life as an academic, which has been a long time now. And so that's sort of some of the things that I'm going to be talking today about. How do we advance humans and robots, human-robot communication? But before I start, I have an advertorial. We've just released a book led by Laymin Tan from CSIRO, which is the Australian Commonwealth Scientific and Industrial Research Organization, and a bunch of good friends from Monash, and some of you may know Dana Kulit. She was in on the party. And we've put this book together for you. So if you are interested in doing research on human-robot interaction, this is like the cookbook. What it does is it steps you through the whole process of doing human-centered robotic studies, starting from your research questions all the way to how you set up your study model, your evaluation methods, the feasibility around tools and equipments, participant methods, there we go. How you recruit participants, the dreaded study protocol and ethics procedures. For many of us, this was like, oh my God, how do I do this? I'm not doing a clinical research trial and I'm not giving people drugs, so how do I fill out these forms? What does that mean? All the way to conducting pilots, recruiting participants, measurements, a bunch of stuff on data processing and statistical analysis, which is super fun, and a nice chapter on reproducibility. So if you're interested in this, and that QR code will get you to the page where we put the book for free. So you don't have to pay CRC Press, don't tell them I told you this. You can get the book online and this interactive tool to help you with your HRI studies. So that's my little advertorial and present for you today. Okay, here's my other advertorial. You know, it's a good place to work. It's a good place to study. It's right on the ocean. It's very nice, and it's warmer there than it is here today. And it's absolutely stunningly beautiful. Okay, so today's talk, human-robot teaming. Can I do that? Or is there a, I'll assume you can hear me. I have a tendency to roam, so I'll try to stand still. These are all the things when we talk about humans and robots working together. I think the centerpiece is that we have to agree on what we're up to, right? So that's the core piece. The pieces that we're going to talk to today are some of the important pieces around this area that help us come to a common purpose. So it's important that we keep robots designed safely, and there's a lot of people that work in that safety area, I know here as well. It's important that we think about ethical robots and AI, and I know, you want to talk to AI. I don't know if Shalalay's here. That's her jam, but lots of good people working in that area. AI and explainability, super important. Interfaces, another huge area. Today, what I'm going to talk to you about is implicit communication. That way of communicating with agents that body language, that communication that we as humans do so well. And right now, between humans and robots, we do so poorly. I'm going to talk about explicit communication, but not the verbal kind, the nonverbal kind, the ways of how do we get robots to get our attention, to communicate what they're doing, using more explicit methods of talking to us. And then the last thing I'm going to talk about is how do we help robots when they need help to do new tasks? How do we think about training users who may not know how to use a robot and then getting them to train robots to do the things that they want? So those are the things that I'm going to talk to you today, all based on work that basically some amazing, wonderful graduate students did, and try to bring those themes back together at the end. So let's start with implicit communication. This is work done by Haoyang Zhang, who just finished his PhD at Monash. Brilliant guy. And what we're talking about in this work is implicit or social robot communication. We want to be able to interact with robots in a way that is legible and adaptable, which is easily understood and socially acceptable, and ideally doesn't require us to explain everything about that implicit interaction, because everybody's implicit interaction in different cultures and societies is a little bit different. So how can robots learn or use the data that we are exuding as humans all the time to figure out how to interact with us? So I'm looking at this question of implicit communication, and when I think about implicit communication, just like explicit communication, it's an exchange of information. And how do we measure communication? How do we measure whether information is actually being passed? Well, in the communication world, they use a concept called transfer entropy. And that is a statistical measure of how much information is going from one data stream to another data stream. So what does that look like? We're going to look at how we detect it, how we measure it, and how we modulate it. So let's look first of all at detection. So the idea is that somebody is doing some kind of activity, and that encoded in that activity is information, And what we are trying to do is measure how much of that information is influencing the other agent. So that looks like this. We have two agents, X and Y, with data that they're generating. Maybe I, as X, am handing something over to you as Y. And the way that I am generating my motions is a data stream. And I can look at that data stream and I can predict what I am going to do next based on my own data stream, right? I can just look at my past and predict what my future will be. And that is basically assuming what, oh, I didn't mean to do that. Let's go back. That's this one here, okay? What I am doing next just based on my own behavior. This data stream is what I am doing next based on my own behavior and what Y is doing, the other person. The difference between those true predictions is transfer entropy. It's the extra information that Y is providing to X that influences what X will do next. So we take that, and that helps us identify where Y is sending cues to X. And we can do it the other way. We can do exactly the same thing where we see what Y is doing based on its own stream, and then we see whether we can predict better what Y is doing based on its own stream and X's stream, and look at the transfer entropy there. And what we can see is that the transfer entropy, or what I would call uncertainty about what the ego agent, or what X is doing, changes depending on whether you use the information from the other agent or not. And that's where we see a cue is transmitted. Information was transmitted. So we can look at that in space, and we can look at it in time. So let's have a look at what this looks like in a handover task. So as you know, some of you will know that I spent a lot of time thinking about handing things back and forth between people. And one of the things I was really interested in is the fact that in some experiments that Ajahn Moon did, we saw that if people handed things over in a certain way, the responder to that handover was ready to receive it sooner than if it was handed over in a weird way. And so there was obviously something going on about cueing, because they weren't talking to each other when they were handing over, they were just passing stuff back and forth. So, and how can we detect that and see what that information is without manually trying to search out the data and look for the cues? Can we find this in any data stream, a cue, just from seeing how the two streams impact each other? And the fact is, we can. We see this measure of transfer entropy. So this is the giver giving stuff to the receiver. They are sending a signal. The receiver is now, its behavior is now getting the signal because it's seen what the giver has sent, so it receives, and then when the giver lets go, then there's a response from the receiver. So we're seeing these changes in transfer entropy back and forth between the partners. And when we change when we do quick handovers, we see that the cues move. When we delay handovers, we see the cues move in time because this happened at a later time. When the giver won't let go, we see that the cues related to handover stretch out. And when the giver uses a weird pose to hand things over, the cues get muddied. So we can see that just by looking at this measure of predictability, this measure of the difference in predictability, which is a measure of entropy, we can identify where the cues occur. So we no longer have to look at the stream and try to pattern match. We can just look at this. Does this work in other places? So we did this very bizarre experiment where we had people, a leader and a follower. So the person A had somebody behind them, and they had to figure out where B was going while they were in front of B, whether the B was going to go straight, left, or right. And what we could see is that both of them were communicating to each other before the turns happened. So B, who is the leader, was already sending information here to A, communicating the goal before they got into this place where they turned. A was providing information back to B. We could see the change in A and B's trajectory closer to the goal, where they, oh, okay, I figured out and I'm gonna go that way. So we could see these cues of information being passed between the two streams just from how they were moving, just those data sets. So then we also looked at group joining. So there was a lot of information from the new member. That new member joining a group provided an influence on the group. The group did not provide influence or change the way that the person joining it did, but the joining person, their motions provided an information transfer to the group. So in each of these things, we stop looking for specific cues, and what we look for is a change in behavior between of the streams of data that we're just getting from each of the members, each of the members of the interaction. We look for that measure of the difference between what I can predict of that person's behavior based on their own data stream and what I can predict of that person's behavior from their stream and the other stream, and see if the predictability is better, the entropy is less, then I've seen a cue. So that's the idea. How we use it is the next thing. So this tells you when, where, and the direction a social cue occurs. How do we take that information and then apply it to a robotic system? So we use this idea of transfer entropy as a reward in a reinforcement learning framework. So we calculate as I said already, the information transfer from the past actions of other agents to the current action of the agent that we're influencing. So that's or what we call the ego agent. And we add that to their reward. We say, you will get more reward if you are receiving information. So look at that information. And then we scale that based on that phi. If you're not influenced by the other agent, then you're just getting your reward. If you are providing information, then you get a high reward for transfer entropy. And if you are hiding information, then you get you have very little, you're not influencing, then you get a low reward. So we have these three types of agents, and we get them to play the corridor game. So this is purely agent versus agent to start with. The corridor dilemma is two people walking down a corridor, they meet in the middle, and they have one of two objectives. They either want to meet their opponent, or they want to avoid the opponent. And so if we give the objective to each agent, whether they want to meet or to pass, and then they play the game. So if P1 wants to pass and P2 wants to meet, and they end up in this situation, then P1 has won the game because he hasn't met P2, and P2 has lost because he hasn't met P1. If they are both meet, then P2 made its objective and P1 did not. So there's 4 possibilities, obviously, both pass, P1 meet, P2 pass, P2 meet, P1 pass, or both meet. So we have 4 different possibilities, and we play this game in simulation over and over and over again. We try it with these different agents. We try just an agent that is not influencing. We try it with agents that provide information, and we try it with agents that hide information. And what do we see? So it's interesting. After we train the agents and they play, the agent that is just a standard, just learned the game but had no influence of transfer entropy, does really, really well when playing with an agent that is sharing information. So that's where we get this. When in competition, it does really well, which kind of makes sense. If I'm playing with another agent and it's providing me extra information, it's influencing me, I will do really well. I also do well in collaboration. When 2 agents are both sharing information, they're basically fair in competition, but in collaboration, they both win a lot. When an agent is playing that is hiding information, and it plays an agent that is sharing information, in competition, it wins much more, because it's able to basically manipulate the other agent, I guess, or use that information. So that's from simulation, and our question is, can we use this with people? Does this work? So to recap, a positive transfer entropy agent which encourages influence enhances the outcome for the other agent in cooperative and competitive settings, and an agent that hides information, suppresses their influences, reduces the opportunities, the performance of the other agent. This is what the results look like. So here we have, just for an agent that is not trained on transfer entropy, playing these 2 different types of agents in collaboration, very successful. In competition, successful, but the difference is not as much. How does this look like when we do it with people? So we got people to be one of the agents in the game. Same idea, and we had 26 participants, because we went through and we figured out how many participants we needed, so go back to the book. And these participants played a positive TE agent, a non-TE agent, and a negative TE agent, and we wanted to see how well they would do. And we did see that when, in collaborative settings, when a human played a positive TE agent, an agent that was sharing information, through transfer entropy, as measured by transfer entropy, and trained to do that, the human did better. They won more games than when they were playing an agent that was trained through transfer entropy to hide information. Now, we didn't see a result for competitive settings, which is kind of like what we saw with the simulation, that the result is more muted. So, and then we asked some questions just to see what people thought of these agents. And we saw, I don't think these are strong results, but we did see that people did, from this measure, think that the robot was, the agent was more clear about what they were trying to do. They could understand their strategy more, although we don't actually know what the strategy is. It was just trained for reward to win. And they more likely thought that the agent that they were playing, because we didn't tell them, was a human. Does it work with real robots? Same game, this time a fetch versus a person. So we used the same agents that we'd already pre-trained to either share information or not share information. And we ran the thing again. They had to walk a lot. They had to play the corridor game 80 times, which is a lot. And what do we see? Not quite there. Our P is 0.057. Ow. But, you know, on a trend level, people were winning more games with an agent that was sharing information than with a robot that was hiding information. No difference in competition. So, and less information, I would say, about whether they thought that the robot was human or not. It's unclear. So what do we get out of this? So we have a framework now that just takes the data stream and sorts out where the cues, the implicit cues, are in that data stream without defining what those cues are. And we validated that those cues exist in both human settings and human robot settings. And we are now able to take that framework and train robots to share information by before they interact with people, through training them on simulations, without knowing what cues the robots are actually sharing. So we validate it in the human agent situation, and we think we have a strong hint for HRI, for human-robot interaction as well. Where do we think this could be really interesting? Potentially in areas like autonomous driving, interacting with robots on sidewalks, where we train the vehicle, whatever that vehicle is, to be showing what it's going to be up to next and trying to influence the behavior, to be more influencing in its interaction without having to know what that cue actually has to be. So that's kind of the take home for that. Where do we go next? More experiments. One of the things that I think is really interesting we also found is this works in collaboration well, but it does not work well in competition. So trying to figure out, well, what are the scenarios? So if, you know, in a driving situation, if we're just trying to all beat each other, that's competition, that's not good. But if we're trying to navigate together so that we're all successful in getting down the road without having collisions, then this could be very, very useful. So it's useful when all the agents want to collaborate. And so right now we are working on driving simulations and seeing whether this can also work with multiple agents. Okay. Okay, so next up is explicit communication. So we've already seen that, you know, we can do stuff with with implicit cues, but with explicit cues, we're looking particularly at nonverbal cues. Obviously, there's a lot of things we can do by conversation, but nonverbal communication is very, very important because we use it all the time. We use gestures, we use body language, we use slides, and we use it to enhance clarity, to add emphasis, and we use it to facilitate quick communication. So, again, the challenge is how do we design these expressions? How do we automate this? How do we make this something that we can use in everyday robotics? A lot of people have worked on manual design, designing motions and cues for different humanoid robots. It's very time intensive, it's not very scalable, and it's confused and made more complex because different cues in body language means different things in different cultures. We've tried, crowdsourcing, getting people, that's a lot of work. There's a lot of labeling that has to be done. Optimization, how do we do that and align it to human perception? LLMs, this is an opportunity, and that can be a bit ambiguous, but we are thinking that how do we bring these things together to design nonverbal cues, robotic expressions? The other big challenge is lots of different kinds of robots. And so how do we make, whether you have a humanoid or, a drone or a sidewalk robot, how do we design those gestures? There has to be a better way. That was what Liam is working on. He's just about to submit his thesis, which is very exciting. So the gap that we're working on is how do we autonomously generate nonverbal expressions for an arbitrary form factor? So it should look at available communication strategies, what the robot can do, and what the context is to create appropriate expressions. So we started using reinforcement learning to say, okay, what we'll do is we'll parameterize the expression space, and then we will get the robot to make all of these different expressions. We will collect data from humans, which is expensive, and then we will improve the robot by, reinforcement learning and figuring out which cues the person identifies, which worked, but we recognize that it's interesting that one of the things we found with that is we could start with one person's generalization and actually speed up the learning by using that as the base for the next person. So that was one of the benefits of that approach. Then we decided, okay, these large language models, they're interesting. Could we get them to select robot expressions? So we provided the model with the robot description, the target state, and a set of parameters. And we just said, okay, if the robot is doing this, what is it communicating? And then we repeated that with different variability and identified what the LLM would consistently choose, and then generate robot expressions. The challenge we had with that is that the LLMs tend to generate expressions that overlap. So while the performance is not bad, some of them look very, very similar. So one of the things we had was found object and analyzing object. Sometimes they would look too similar so that the human could not actually identify what the robot was trying to communicate. So then how could we improve this? How could we make LLMs generate robot expressions and prevent that overlap between, say, found object and analyzing object? How do we quantify a value to a robot's action space without actually getting humans to provide any feedback? So the idea was to not only get the LLM to create the expression, but then get the LLM to optimize the expression as well. So we then use this optimization to select which are the expressions that are best accepted or has highest value, and then the other piece that we wanted to do was to implement a bit of a distance function that would prevent different form factors from lying on top of each other. So this proxy-based optimization. So there's all the mathy stuff, which is actually fairly simple. We have the states, we have which is the S's, we have the motions, which are the E's, and we use the LLM on the first term, which is what the LLM thinks a human will choose of this vocabulary, this position that the robot is taking to express a state. And then we also added a weighting term for how far apart these expressions are. And so the way it works is that we we activate the motion parameters. We ask the LLM, do you think this looks like one of these different states? But when we share that information to the LLM, we randomly take out different pieces of what the robot is doing. And what that actually does is behaves a bit like a human, because people pay attention to different things. So we introduce some noise into the system, basically, and that actually helps the LLM be more reliable in picking out different expressions that look like and expressing what those different expressions are. So we put those in, we create the pose after the omission, we provide that to the LLM, and then the LLM selects the state. And what we found when we did test that against the humans is that this proxy actually aligned very well with what people said the behavior of the robot was. When people were very convinced that the robot was waiting for input or analyzing object, the alignment was really good. When things were inconsistent, so for example, here we've got needs help or confused, those two seem to get overlapped. Both humans and the LLM also had that same kind of confusion as well. So basically what we found is this human proxy for saying what it thought the robot was trying to communicate was certain when people were certain and not certain when people were not certain, I guess. So the alignment was very well. The other piece was how we can separate poses or in space. We looked at both Earth movers distance, which is just sort of like how far you are apart based on the parameter space, and we looked at kinematic distance, which is what we all understand as kinematic distance, how far the joints are apart. And then we optimize that. And so we took all of the different optimized outcomes for the different kinds of expressions that the robot could do. So this one that was previously done by the LLM, the one that was optimized by another LLM, the one that was optimized by Earth mover distance, and the one that was optimized by kinematic distance, to see if we could create a robot vocabulary that people could well understand. we gave them a situation where Go 1 quadruped was using expressive poses to try and tell its partner what it was doing, what it needed. We recorded the videos, and then we had participants watch the videos and then say what they thought the robot was trying to say and how confident they were. And what we found is that by using an LLM to train the initial poses that we got from the former LLM, we definitely had improvement, and that if we wanted to improve, increase disambiguation, if we wanted we wanted over a 5-state space vocabulary to make sure that things like error or needs help is different than confused, then adding a kinematic distance to this optimization improved things a lot for a larger vocabulary. It was not so helpful with a smaller vocabulary. So overall, we see that LLMs are good proxies for humans when they behave like humans, and why it is performing better. So this is what we originally had, that confused and error look the same, but with the optimization approach, they start to look a bit different. In the error, it crouches down more, and it kind of, I have no idea what I'm doing. And in the confused, I think it's actually, oh, sorry. I think it's the tilting that actually gets to people. It's like, I'm not sure, what do you want? Maybe that's what it is. But that's all generated by the LM. We did not create this. This is all generated by the LLM. So when the LLM did this in isolation, found object and analyzing object ended up being the same thing. Adding distance absolutely helped, because found object and analyzing object moved apart. So with a larger vocabulary, moving things apart in the state space helped a lot. In a small vocabulary, we overweighted distance, and so the communication of the form factor of the robot was underweighted. So we learned that we have to, the scaling between moving motions apart and being communicative in terms of what the robot's trying to say, there's a balance there that we haven't quite got right yet. So before I go on, what are the take-homes here? So LLMs, I think my sort of shorthand for this is they aren't really human, right? They're a collection of information about what humans predict what humans might say next, but they're an average. And I think putting noise into what we get out of them, increasing the temperature or giving them different parts of information, helps them behave more like what our human subjects are. So they are really a useful proxy if we think about how humans actually behave. I think that was actually the whole take home. And of course, here is a way to design communicative cues automatically, which is a nice thing for all of us who have been doing a lot of human-robot interaction experiments and spending a lot on human subjects. So that's good. The last thing I'm going to talk about is, and I've got a little more time here, is user training. So if we want to work with robots and we want them to learn to do things in our home and in our offices, We were talking with Steve yesterday about all the different complexities of a manufacturing task, so many different things that we'd like robots to do. And right now, a lot of our things that we do is we structure it and we make it very, very simple. And if we want robots to learn new things, we have to generate lots and lots of data so you can use learning from demonstration, so you can teach the robot to do the next thing. And that's great, but again, if I am a user and I pull this robot out of a box, am I going to have to give it 100 demonstrations before I get it to do the thing that I want? So how do we, working with users, improve users' information they're providing to robots so that robots can learn from demonstration? So it's a little bit of a circle here. We're going to look at 3 different problems. We're going to look at, how do we improve data quality. We're going to look at how we increase efficiency, and then we're going to look at how we improve the way that people learn to provide training demonstrations in these 3 experiments. So, learning from demonstration, what does that look like? We want to work side by side with these things, and all of these examples, we are up close and personal with the robot, and we are trying to get the robot to learn new things in these situations. So we have the information that the robot needs that needs to be communicated to the human, and then demonstrations, and this is the key part, that meet what the robot needs, but it helps people to do this in an efficient and intuitive way. So how do we know that the demonstrations that the robot are providing are of good quality? How do we teach users to improve their teaching skills? And how do we teach users to provide efficient demonstrations that cover the entire space of what we want the robot to do? So we'll start with the first one. How do we know if a demonstration is good quality? We talk about failed demonstrations, unsuccessful demonstrations, imperfect, ambiguous, but we don't have really good metrics to say what is a good human demonstration. So we got a bunch of users to demonstrate something, in this case, this button, getting the PR2 to push buttons. It learns the task from those demonstrations. And then we evaluate whether those are high-quality demonstrations or low-quality demonstrations, and then see if those demonstrations will generalize. So the measure is how well did the robot perform the task? So the button pressing task I mentioned, we had 2 kinds of tasks. One of them was when the robot just had to go and press the button, pretty easy. And then the other one, when the robot had to skirt around the box and kind of press it from the other side. So there's some singularities, there's some collisions. It has to learn how to move around and not knock the box off the stool. So 2 kinds of constraints, 27 participants, and we also collected the data in 2 sessions because we wanted to see about after you work with the robot, if there's a change in the quality of the way that the human is providing these demonstrations. So we used, as I said, how well the robot can learn from the demonstrations as the success metric for the demonstration. So high quality demonstrations gave successful trajectories and low quality demonstrations gave unsuccessful trajectories. So where's the dividing line? So for these different kind of tasks. So we looked at the different kind of tasks. For the low constraint task, lots of the users could provide good demonstrations. For the high, that resulted in successful trajectory generations. For the high constraint tasks, many of the users had difficulty, especially on the first day, of providing quality demonstrations that resulted in good trajectories. So we looked at these violin plots and we said, okay, well, for the first go, what we'll do is we'll say, looks around 80%, you get high quality, and those are the ones that give us most of the weights of good trajectories, and below 80%, we're getting more failures. So that's how we cut it apart. Okay, so that's our ratio. Those are the high quality, and below 80%, low quality. So we divided those up into 2 sessions, high quality from the first, high quality users from the first session, high quality outcomes from the second session. We called those the fast adapters, and then we had users who provided low quality from the first session, but then they improved, and they had high quality demonstrations in the second session, so those are our slow adapters. And that's just basically what came out of what we saw from our group of our participants. What's interesting about these participants is that 50% of the fast adapters said they had previous robotics experience. So there are some people who had no robotics experience, half of them, but were really good at moving the robot around. We had 25% in our slow adapters group also said they had previous robotics experience, and they were really crap at moving the robot around. So what people say has nothing to do with what actually their skill level is, but we already knew that. So what this take home is that just because somebody says that they know how to move a robot around, we should actually, the proof is in the pudding. How good are their demonstrations? And that's how we should assess whether the information that we're getting from a user is actually useful for reinforcement learning. So we then looked at the success rate from the tasks, and what we could see is in both the slow adapters, in the low constraint task, and in the high constraint task, they pretty much caught up to the fast adapters by the second session. So we can see, yeah, here they are, both sessions, they improve quite a lot. But there's really a significant difference in how they perform in the first session. In the second session, no significant difference. So what we're seeing is that users can adapt to tasks, but they need practice in order to provide high quality demonstrations. And this fits with the Fitz and Posner model that shows that over time, and this is, so we did two sessions, and that was really important, is to show that we can get people to, even people who have no experience, we can get them to become quite good at providing demonstrations if we do multiple sessions. Okay, so this is just sort of how they're going along. I'm going to move along because I'm getting a little behind here. Does quantity, so does this idea, well, it doesn't really matter. We don't have to train people. We'll just get them to give lots and lots of demonstrations. Will that compensate for quality? No. So we took 9 high-quality demos, and we took 54 high and low-quality demos, and we trained the robot on those demos. You had much more successful trajectories out of the 9 high-quality demos than over the mixed quality demos. So demonstration quantity does not compensate for quality. You actually want to have better demos. So quality is important. It should be assessed. That we should look at how we, now, and that's a question, how do we assess quality? Users adapt at different rates, and they need some practice, and quantity does not make up for quality. So, how do we define whether a demonstration is good quality? So, we looked at taking that same data, we used inverse optimal control to extract cost functions from high quality and low quality data. And looking at these cost functions, we wanted to see what were the factors that contribute to the effectiveness of these demonstrations. So we took the high quality demonstrations and the low quality demonstrations, and we wanted to see the different pieces that we looked at. So what we said we wanted to look at manipulability, so we stay away from joint limits. Manipulability, so we don't get caught in singularities. We want to look at distance to joint limits. We want to look at how long they were taking together, in terms of path. And we looked at the fast adapters, and we looked at the slow adapters. The fast adapters, if we look at their plots, what we see is that there's not a lot of variability in how they are moving through the trajectory. If we look, they basically use the same strategy each time, and they got consistent results. So these are the different things that we're plotting here: manipulability, path length, very consistent. If we look at slow adapters, they are not consistent. They are all over the place. Lots of variability. Got a little bit better in the second session. You can see over here they got more consistent, but a lot of noise, because they're trying different strategies to figure out how to get the robot to move, so they get fluctuating results. In the end, they converged more with manipulability. Sorry, I pushed the wrong button there. Manipulability converged more, but certainly the expert ones, or the fast adapters, provided better results. So, the absolute values, because they all got there, did not give us any correlation to success. So this is what we see from a low constraint and a high constraint button in terms of the manipulability and the distance to joint limits. No consistency in the absolute value. But what is it? So absolute value does not tell us anything, but the consistency, how repeatedly they did the task, did give us good results. So what we did is we took the users, we clustered and their trajectories, and we changed them we divided them up. Instead of fast and slow adapter, we divided them up into consistent trajectories and inconsistent trajectories. And then we looked at all of them, and it's interesting that on all the different attributes that we wanted to look at, whether it was manipulability, jerk, legibility, well, actually, legibility was pretty much similar, but all the other ones, there was differences in the consistency, the repeatability between the attributes. Especially, you can see with path length, with orientation, with jerk, manipulability, between the consistent, the consistent ones and the inconsistent, a really significant difference through clustering. So they have a low range, small distribution because they're consistent. Whereas the inconsistent, high range, wider distribution across most of the metrics. And then we look at task success. If we take consistent demonstrations and inconsistent demonstrations, what do we get? We get much higher success rate with these consistent demonstrations. So we can now go and look at people's demonstrations and say, if they do things repetitively, not repeatedly, but in the same way, if they don't have a lot of variability in how they show the robot, in the trajectories that they use, we will get better outcomes. So consistency is a measure of quality, and it means that we can use a smaller number of examples without the need for running and knowing that they're going to be successful without actually testing it on our learning algorithm. We know those demonstrations will be good. So consistency matters. So how do we enable users to provide those consistent trajectories? So we tried 2 training techniques, one using video and one using kinematic data to train users to provide consistent trajectories. And so one was basically you come in, you watch a video, and then you try to do the task. The other one, you hold on to the robot, and the robot guides you through the task. So kinesthetic training, hand over hand. And then we also introduced a third group, which is discovery training, which is basically come in, try to figure it out, play with the robot. And what we did is we found that we first see how the person trains the robot, their first interaction. We do the training in one of 3 groups. We see whether they are able to do that task after they were trained, and then we try it on a different task. So the training task is a pick and place task. The transfer task is getting the robot to draw lines within a boundary. What we found is that with the observational, showing people how to do it, they actually improved over the retention test. Which was interesting is after the sessions, everybody was able to do a better job in the transfer task, which is drawing the C-shaped object. So we were able to, by teaching people with observation or kinesthetic, improve the quality of the kind of demonstrations that they did. And then in the transfer task, it was an easier task than the original task, so the discovery group was also able to take the learning they did from playing with the robot and improve the kind of trajectories they were providing. So the takeaways, training groups gives you, with exposure to expert data, it's higher skill retention on the difficult task. Kinesthetic training gave us the most effective results. Discovery training did improve performance, but it took more time for their practice. So I am getting close to end of time here. In fact, I probably am at my end of time. So I'm going to skip through the next one. And I'm just going to, which was about how do we show people how to, how to give them more efficient demonstrations, which again uses entropy. I will refer you to another paper, sorry. And I will skip through to the take-home of this. Sorry. Okay. So some take-home messages here. So where we just came from, improving user performance will give you better results. Even a small amount of training, it helps, and the training is transferable. We can quickly identify good user input by measuring how consistent people do tasks. So by doing that, we can show users that if they are repeatable in how they show the task, they're going to generate good data, and then we don't have to produce lots and lots of data. We can produce a small number of demonstrations that the robot can learn from, and the robot will be able to do the task quickly. The last stuff that I skipped through, the take-home message from that is if you use entropy again to differentiate what kinds of demonstrations a user provides, you can also allow the robot to get examples, consistent examples, but over a larger space. Another talk, another day. LLMs. They are interesting proxies for generating human data. And they offer this opportunity both to generate cues and information because they take the average of what people will say, but they can be too perfect. And so if you want to represent actual users in generating cues and gestures, at least what we found, is that you want to recognize that people pay attention to different things. So injecting noise, which is effectively what we did, into the LLM helps you create more of a human response and more of a proxy for a human in an experiment. So they can be too perfect. And of course, we should be aware of that. The corpus of LLMs that we have right now are really representing a Western, North American, European view of what things mean. So it'll probably fail terribly unless we start creating LLMs that are based on other cultural norms. And then lastly, and I think this is the fun one, is that if we increase predictable robot behaviors by maximizing the communication, the transfer entropy, we train robots to be more expressive by just measuring how they communicate implicitly. By increasing this measure called transfer entropy, they will help the humans that they're working with be more successful in collaborative tasks. So this gives me a lot of hope because we don't have to design this, we don't have to pick out the cues. We can actually use reinforcement learning training to just get robots to expose their intentions, if you will, through that training. And so that's, sorry I went a little long, but there are still so much to do. There's so many lovely shiny tools out there now. Don't forget some of the old tools. Information theory, entropy, there's a rich opportunities for lots of things to there. But I think the last thing I'd like to say is that responsible and scalable robotics, it's a persistent challenge, but if we think about people in our design and in our work, we can move to a place where robots truly will help us, will work with us, and work for us. So that's the end of my story. Thanks so much. And